last discussion of the workshop program.
Should be, yes. Which is the name of your presentation?
IWHALM15 and well, it's not me in the first place.
Yeah,
So I'm going to call for the first presenter, Mr. Bowen. Yes. Good morning, everyone. I will be chairing this first session this morning, and I would like to thank you for attending, being here. I'm calling Ms. Bowen for the first presentation. Thank you. You can use this one or this one, the way you want.
Welcome to my talk, A Conventional Explanation for Palladium Deuterium LENR with Considerations of the NAE and Secondary Reactions. Currently, low-energy nuclear reactions do not have a good technical explanation, at least not one accepted by conventional physicists. I'm going to give you a preview of the conclusion. This is a conventional explanation for LENR without needing any kind of unusual physics or theories. Here is the outline of my talk, a brief review of my previous presentation, a description of NAE, and then a calculation of an example reactor, followed by a look at neutron emissions. And the arrows, okay. I want to start with a review of my previous talk on this topic, primary and secondary reactions in an LENR. Now, some of you might think that the concept of primary and secondary reactions is strange. However, the concept that more than one reaction might be occurring in a reactor is not bizarre. Actually, the converse is true. It is quite incorrect to think that there's only one reaction occurring in a reactor. All nuclear reactors, fission, fusion, hot, cold, have many reactions occurring inside the reactor. The two primary reactions are the usual ones seen here. These child products go on to react in secondary reactions shown here. There's no gamma radiation, no neutron suppression, no enhancement of the D2 to D2 to H4 plus gamma reaction, no need for unusual physics to explain how to overcome the Coulomb barrier. I show that standard physics and conventional engineering can explain it. Now, just as is occurring in a fission reactor, the nuclear byproducts of the reactions are what sustain the chain reaction. The mechanism is that the child products collide with the cold D2, doing so frequently and energetically enough to sustain the D2 to D2 reaction. If the conditions in the core are right, then from that very first initial reaction, the reaction rate will grow to steady state. Unfortunately, that very first initial reaction is caused by fairly random external events. The nuclear active environment, or NAE, is critical for LENR and should not be ignored. Although it is experimentally confirmed, it is not well studied. The NAE is not a flawless crystal lattice. Rather, it is the defects in the lattice that create this optimum environment. It has a concentration of D2 estimated by storms to be about 10 times more than what is in the lattice. These crystal defects are created during the loading process in the form of cracks and fissures. The formation of the crystal defects is dependent on many factors, shown here. However, the optimum values of these parameters are unknown. Inside the palladium, the D2 is ionic and interstitial. Inside the NAE, it is atomic or molecular. It cannot re-enter the lattice, which is why it has a high density. Let's look at an example of an LENR using some reasonable values. 1 watt of power from the 2 primary reactions. The D2 density in the NAE is 10 times the value of the palladium lattice at 100% loading. This gives 2.2 grams per cubic centimeter. The total NAEs have increased the sample dimensions by 20%. The released energy of both the primary and secondary reactions is the kinetic energy of the child products. This energy is transferred to the cold D2 via collisions, allowing a subsequent D2 to D2 reaction to occur. Negligible energy is transferred to the palladium lattice. For 1 watt of power from the primary reactions, the reaction rate is 1.71 times 10 to the 12th reactions per second. Charged child products stay in the NAE, but neutrons do not. I will discuss the fate of these escaped neutrons toward the end of the presentation, after I calculate the possibility of a chain reaction. This calculation is done in 4 parts. Part 1, determine the number and average energy of the scattered D2 from the primary child products. Part 2, determine the reaction rate of the 2 secondary reactions. These first 2 parts will be the most time-consuming sections of this talk. Then things will go much faster. Part 3 repeats the scattering calculations for the child products of the secondary reactions, and Part 4 determines the reaction rate of the subsequent D2 to D2 reaction. All of these calculations use conventional engineering to make these determinations. Here's a brief overview of scattering for charged particles. It is similar to Rutherford scattering, but without the approximations. The calculations must be done in the center of mass reference frame using reduced mass. Here are the equations for that. The final velocity of the projectile can be found, as well as the final energy. The energy transferred to the target is the difference. Our first goal is to find the number of successfully scattered D2, defined as a transfer of 0.1 MeV or more to a cold D2. A second goal is to find the average energy of these successfully scattered D2. To achieve these 2 goals, we need the impact parameter, the scattering cross-section, and the probability function for scattering. The probability function for only one angle is shown here. The probability function combined with the energy function allows us to calculate the number of successfully scattered D2, as well as their average energy. The curve here is the experimentally determined reaction cross-section. The blue curve is for D2 to D2. As you can see, the reaction decreases as the energy goes down to lower energies, but it does not fall to zero with a cliff-like drop-off. At lower energies, there is still a non-zero probability of a reaction, and this is what we want to utilize. The blue arrow here is where the reaction rate has fallen off to a level too low to be considered important. This is 0.1 MeV of energy. The equation for the average energy is this. Using the appropriate integration limits. Theta center of mass max is always 180 degrees. Theta center of mass min is found using this equation, and theta center of mass success is found using this equation. For the angle theta center of mass, these integrals are then solved using numeric integration, as shown here. To find the number of successfully scattered events, this equation is used. Again, this is solved with numeric integration. Here's a small sample of a very large table used for numeric integrations. This table is used just for protons. A similar table must be made for every projectile type. These numeric integrations are done for every energy that the projectile passes through as it thermalizes. I show this in the next slide. I realize these numbers are too small to see, but I want to show you that I have done these calculations and that these numbers are real. Here, the numeric integrations for the protons are done as the energy steps down from 3.03 to 0.1 MeV. The results are shown here. Here, the numerical integrations, the results are that the successful scattering event is 3.058 times 10 to the 12th with an average energy of 0.278 MeV. Here I have repeated everything, all calculations, numeric integrations, and energy ranges for the projectiles of tritium and He3. The values are highlighted in green for the numbers and average energy of the successful scatterings. For T3, there are 7.95 times 10 to the 11th at 0.2084 MeV. For He3, there are 6.07 times 10 to the 11th at 0.197 MeV. Next, we look at neutron scattering, different from charged particle scattering and easier. It uses experimental data for the cross-sections. A fixed amount of energy called the logarithmic energy decrement is lost, on average, for each scatter. As before, we are only interested in energy transfers of 0.1 MeV or more. This table shows this information. The number of successful scattering events is 3.58 times 10 to the 11th, and the average energy is 1.026 MeV. Next, in part 2 of this calculation, we need to calculate the reaction rates for the secondary reactions. The standard equation is the product of the density of the target, the cross-section of the reaction rate at that energy, the projectile velocity, and the projectile density at that energy. The difficult parameter here is the projectile density. The projectile density is its introduction rate at that energy multiplied by the time spent at that energy. To solve this, we need to know the average number of times n the projectile scatters and the average length between scatters, L, for the average angle. However, that average angle is unknown. Thus, the L times n product must be multiplied by the probability for that angle, then summed, and then normalized. This will be the distance the average projectile travels in the core for all angles for one energy. That distance for one MeV is calculated and summed for all angles, highlighted in yellow. That one value can now be used to determine the reaction rate for that one energy step. For the T3 to D2 reaction, the energy range is from 1 MeV down to 0.01 MeV, as indicated by the red arrow. That distance for one energy, all angles, is solved for 18 different energy steps within this range, shown here in green. Not very bright green, but that is supposed to be green. We use these steps at the bottom of the table to calculate the fusion reaction rates. The reaction rate for the T3 to D2 reaction is calculated for each energy step, then summed for all energies. For the numbers used in this example, the reaction rate is 68.4%. This entire procedure is repeated for HE3 to D2 reaction, giving a reaction rate of 21.74%. A total of 2.19 watts is generated from these two secondary reactions, and 4 new energetic child products are produced: helium-4, neutrons, more helium-4, and protons. The overall heat to helium-4 ratio for the palladium core is 25.88 MeV per helium-4. These 4 energetic child products scatter with the D2 just as the previous child products did. The same equations and procedures apply using appropriate values. The final results for both the primary and secondary reactions are shown here. There are 1.082 times 10 to the 13th energetic D2 with an average energy of 0.399 MeV. Recall that I picked the D2 density in the NAE for this example to be 10 times the value of 100% loading. The chain reaction requires at least 1.71 times 10 to the 12th reactions or more. We get 1.752 times 10 to the 12th. With this density, a chain reaction will occur. Before we make any conclusions, let's examine the neutron emission from the LENR setup. I want to consider 2 types of neutrons, thermal and energetic. Thermal neutrons have a much larger reaction cross-section. There are not many thermal neutrons in the core, but for the few that are there in the core, There are two main reactions that absorb the thermal neutrons, shown here. For thermal neutrons outside the core, but still in the setup, there are three reactions of importance. This lithium reaction is used in hot fusion reactors to prevent neutrons from escaping due to its large thermal cross-section. And lithium is typically used in an electrolytic LENR setup, and more He4 results from this reaction. Also, the boron 10 in the borosilicate glass removes thermal neutrons with a huge cross-section of 3,840 barns. For a setup that contains any borosilicate glass, thermal neutrons will get absorbed by it. Boron 10 is used in fission reactors as a moderator. As you can see, there is more He4 released. The third reaction is the water bath with a high density of hydrogen. Again, this is a moderator for fission reactors, and it is also used in most LENR setups. Deuterium is created. The result is that thermal neutrons will not escape the LENR setup. But what about energetic neutrons? Most energetic neutrons will escape the palladium core before they thermalize. When they enter into the electrolytic or water bath, they scatter. If they scatter once, they lose about half of their energy. So if a neutron scatters once, its scattering cross-section becomes larger, and it is more likely to scatter again, and again, and again, until it thermalizes. The test then is to see if all of the highest energy neutrons at 14.07 MeV scatter at least once in the setup. Let's do the math. Here are the calculations. Here are the conditions for the example calculation, again, using reasonable values. The whole setup has a radius of roughly 1 foot. Here are the results of the calculation. The rows of numbers represent the percentage of scattering that occur in the palladium core, the electrolyte, the Pyrex, the water bath, and the second Pyrex. As the energetic neutrons move through these layers of the setup, all the elements in these layers are included in the calculation for scattering probability. In green on the right, the total percentage of neutrons that do not scatter is calculated in a running total. The water is the main component that scatters the neutrons. For the setup in this example, all neutrons scatter at least once. The negative numbers circled in red means that some of the neutrons have scattered twice. The net result is that no neutrons arrive at the outer Pyrex beaker without scattering at least once. Some neutrons may indeed be able to escape, but only a minimal amount. The reason we don't see many neutrons leaving the setup is because the typical setup scatters and absorbs them, just like in a fission reactor. Now it is time to make some conclusions. All the, quote, miracles of LENR are explained, seen here. No unusual theories or new physics are needed. Just apply conventional nuclear engineering and standard physics to the issue. And the answer is yes, LENR is possible. What is different in this analysis is the inclusion of the secondary reactions in the palladium core and the understanding that the NAE must be considered. Most important, No longer can anyone say that there is no conventional theory for LENR. It is explained using standard physics and conventional engineering. Thank you.
Any question?
Okay, very nice talk. Just one question. If I have well seen, to start this wonderful reaction is needed a concentration of deuterium in palladium factor 10. How to reach this number?
How to reach a concentration of 10? Very good question. Let's see. Why are low energy nuclear reactors so intermittent? My second bullet point there is the high density of deuterium is difficult to obtain, and this is an excellent place where more experimental research is needed to determine how best to achieve this high density. Now, I didn't expect any of you to be able to look at those equations that I put up there. I put them up there so you could see that they do exist, and I'm actually using mathematical equations. But if you look at those equations, they mostly contain constants and things that we are not able to change. There's only one little knob there that an experimenter can use to alter the reaction rate in his or her setup, and that's the density. So it is important for us to figure out how to create a high density. Now, Storms in his book claims that 10 times the lattice density is what is achieved in NAEs. But I think this is one of the reasons why LENR is so difficult. As you can see, another reason I put up there, the first one is that very first initial reaction, the very first one inside the core, is dependent on external mechanisms. So sunspots, how much radon is in your foundation, cosmic rays, etc. So it might be better to include a little piece of a starter in your reactor so that you're not dependent on random events. Any other questions? Oh, yes. Okay.
Okay, I like it, your presentation. It's a very good idea to discuss, these primary reactions and secondary reactions. It is what definitely could take place in the reactors. The problem is, however, the first reaction you have mentioned here, that is the starting point. So there is something external. There is not DD reaction. If you are studying DD cold fusion, there is something external, yeah?
That's correct. That first reaction is the difficult one. And I think that's why some of the reactors that we've seen, for instance, in the ICCF 24, there were some experiments that were done and they did not get any result. And I'm guessing, I don't know, but I'm hypothesizing that perhaps those reactors were too well shielded to the point where they were not allowed to get any cosmic rays or fast ambient neutrons coming into the reactor.
What would happen if you start with the usual DD reactions and then you know what can be reaction rates at thermal energies, and then only energetic products of DD reactions are neutrons, protons, and helium-3 particles, and then you continue your calculations for secondary reactions. This one point is maybe the idea you can start to do. Another point is if you're scattering calculations, you have used so-called nuclear stopping power. This is something, the energy loss because of the scattering. Even in that situation, at very low energies or not so low energies, you should use screen potential between interacting particles, so-called nuclear stopping power should include this as well. At very low energies, not, but I don't know exactly what energies you have calculated. That's one point. If you calculate scattering process once again, you should take into account electronic stopping power as well. So energy loss because energy transfer to the electron gas inside, you know, beta Bloch formula. Right. So then I don't know, that can influence your calculation as well.
For neutron scattering, that's experimental, and any electrons that might be in the material would be taken into account. For the calculations that I used, which were for the charged particles, the palladium, when a particle scatters through the palladium, because of the mass difference, there's not a lot of energy difference, or not a lot of energy transferred to the palladium. And I'm talking about what is going on inside of the NAE rather than in the palladium itself. So the palladium is just a container that holds that NAE. And the scattering equations that I used are basically Rutherford scattering, where a particle is going through a foil, presumably with electrons in it, and that those scattering rates are fairly much how you calculate that scattering, without a lot of consideration for the electrons. But in Rutherford scattering, of course, there are electrons. But again, in that situation, they pretty much do not need to consider the electrons, because it's like shooting a bullet through tissue paper. It just doesn't really affect things.
We can speak later about it, okay? Thank you.
Okay, very good.
Okay, about point one, third, before, in our palladium experiment with wires, we coated the surface with thorium nitrate and some glass. But the thorium is mainly gamma emitter and some alpha at the beginning. So when you use americium, the uranium is just alpha emitter. This is your meaning. The gamma can be useful or not? My question, the gamma can be useful for the startup, or is better always alpha?
If the gamma is energetic enough,
thorium may be up to MeV, more or less, 2 mega electron volts, thorium lines.
It would have to transfer enough energy to be able to produce a high energy particle within the palladium core, high enough to start a reaction, high enough to deliver enough energy to some cold D2 to start that reaction. So yeah, starting the reaction is a tricky point, definitely. And was there another question?
And then we will be done. So that's it.
In 1989, there was a group of people in France at the French Atomic Energy Commission that used a neutron source to trigger the reaction. And they saw it. When they remove the trigger, it stops. When they put the neutron, it works. So that's a good indication.
That's very interesting.
I can send you the reference of the paper.
Okay,
It was published.
I will look for that. Thank you. Okay. And Bill?
As I understand it, you're modeling a bulk effect in the palladium, and therefore you would not expect very much helium to escape from the bulk, because helium does not diffuse. So the predicted heat over helium ratio ought to be extremely high, and consequently this model does not represent the observed fact that approximately the heat over helium ratio is around 24, 25.
I believe that helium to heat ratio, heat to helium ratio, is when they pull a vacuum on the sample and pull all of that out, and then they measure the helium.
it's also done continuously. For example, Daniele Gozzi was passing pure nitrogen through his electrolyte to take off the helium, and it was measured in real time, and the same ratio comes out.
Okay.
So that makes it look like a surface effect, and the surface effect is a bit different from a bulk effect.
Well, I would predict that a lot of this is occurring in the NAE, and most of those occur near the surface, within a few microns of the surface. So, yes, you could consider it to be primarily a surface effect. And to the extent that the numerous experiments have then calculated that heat to HE4 ratio using various methods, as you mentioned, but pretty consistent that what they see is around 24, looking at the slide, is around 24 MeV per helium atom. And that's what I'm seeing. And that is actually not a coincidence. If I have, it's more of a cascade effect. If I have two deuterium at a certain energy and they go to an intermediate result of the primary reactions and then they fall again to the final HE4 configuration, that energy between those two steps is the same as the energy from going here down to here. So you would very much anticipate that that energy would be similar to what you see when you do the reaction of 2-deuterium directly to HE4. It's not a coincidence. It's going to be just two steps going down that same energy drop. So it's not a coincidence. Okay.
Let's thank our speaker. Thank you. So, as the chairman of this session, I decided the next speaker will have as much time as he wants. I decide, okay? I can allow myself to do that. No, do good. Do it. Just legitimizing my autocratic behavior.
So, no. Yes.
Sweet.
I will restart it from
You're the boss. Okay, can you hear me now? Yeah? Yeah, the formatting is not exactly the same, sorry for that. My name is Mathieu Vallat. I'm a PhD candidate in Elbrus Lab in the University of Szczecin. I work with Professor Konrad Czerski and his team. I will be presenting the work of Agata Kowalska that has been not been able to come here. This is a work that is into a large group of characterization specialists across Poland, and that involves the Technical University and the Polish Academy of Science in the Nuclear Physics department in Kraków. So what is our motivation in all this? We want to understand in the nuclear experiment how the crystal structure and what role it plays. We want to understand what type of defects are actually enhancing the nuclear reaction rate. And we want to know how do these defects arrange themselves to allow such kind of things, and compare that to the experimental data that we are producing. To give you an idea of how this is all organized, can you see the pointer here? No? I am going to start with that square here. So among all the observations that have been done, one of the greatest observation relates to the increased effective electron mass. This is very central into the evolution of the theory that Konrad Czerski and his team is building. The analysis was very difficult to make, we can assess that this is coming from two aspects. One is the binding energy, the binding of hydrogen to crystal defects, and so this side. And the other one is the localization of conduction electrons. And these two cumulative effects have a modification of the increased effective electron mass. So you can see these observations have been done, especially in that very front at the bottom, that I really encourage you to read with great interest. And it was a 20-year work at Elbrus Lab, at least, actually more than that. The theory of local crystal structure is really important to explain the enhancement of the screening effect. At Elbrus Lab, we have been investigating low-energy nuclear interactions between light elements and metals. And metals are necessary because free electrons are screening the nucleus and increasing the cross-section of the D plus D nuclear reactions. Probably of the D plus D fusion depends on screening energy, UE. Because its effect on the Coulomb barrier, in a very classical way, there is not much non-classical explanation that is used in such development. Experimentally determined screening energy, and therefore the total cross-section, strongly depends on the number of crystal defects in the target sample I was explaining before. So the effective electron mass is the key to nuclear reactions at room temperature. Hence our interest in the crystalline state of the sample. Here we can see on this graph here, we have implantation of deuterons into a zirconium target, and we can see that the enhancement effect is occurring only at the beginning. So something is happening into the crystal, and we want to understand why this goes from here to down here. The proportion, sorry, I didn't expect that to happen. The proportional equation here is derived by Conrad from the Fermi resonance equation. And we have to have a better definition of that equation. And that's part of the work that is related to the understanding of the crystal defects influence on the reactions that we observe. That's why the localized electron increase effectiveness is of crucial importance into this understanding. And I want also to say that the large screening energy measured, they are optically referenced in condensed matter, and it's really something that is not very exotic in terms of science. Conrad makes a lot of efforts trying to explain and stay in the physics, the nuclear physics field in the most classical way you can find, which is very constructive for everybody. The deuteron-deuteron threshold resonance in the compound helium-4 nucleus is necessary to explain the observed enhancement of the reaction cross-section. It was observed that the total cross-section strongly depends on the number of crystal defects in the target sample, hence reinforcing the interest in exploring the crystal defect picture of the sample. Here we have an example of cross-section capture of the cross-section of the DD nuclear reaction, at two different screening energy, at 100 eV and 400 eV. And what we can see is that the resonance aspect plays a major role and in a differentiated way depending on the screening energy that we are observing. And we have this very narrow resonance aspect that are predicted by the theory of Konrad Czerski, and that would help us to greatly enhance the reaction rate by orders of magnitude. So here we have an increase between this dotted line to this peak by an order of 8, and here by an order of 4. We also have, and Matej has presented his paper that is still in the process of publication, about the enhancement factor related to the metallic state of the sample. This is of great interest for me, especially because at the beginning of the cold fusion explorations, we had a lot of people using lamination technique on palladium sample, palladium sheets, to increase locally the quantity of defects. These defects then were acknowledged to be producing and generating better results in terms of energy production in calorimetric experiments. So the very high lamination ratio that they used is showing an enhancement factor that is extremely high, and the calculation is done to actually show with good confidence the baseline. Here we still have an uncertainty, and I have some question actually for you, Matej, about it, but it's certainly going the right way. So why are we using zirconium? In accelerator technology, we are having beam of protons and molecular deuterium to very high energies. And zirconium is helpful in our case because when we stick the deuterium inside the zirconium, it doesn't go out very easily. So we are able to reach a quite significant amount of hydrogen per metal atom, which is very important in terms of evaluating the effectiveness of to have a greater amount of deuterium and then have a greater amount of interactions within the metal. Sorry. We want to observe the defect profile. We also want to understand how carbon and oxygen have been modifying the screening energies. What are the hydride form after implantation? What kind of crystal lattice change have been done, and what are the transformations that happen into the metal and the crystal structure. We have here, and I'm going to present very shortly, this phase diagram. So zirconium has a very special feature. It changes a lot its crystal structure. There is almost every single crystal structure you can find into that phase diagram, which makes the tracking of the forms of hydride at the same time difficult by some means, but also reassuring, because when you have identified the crystal structure, you know where you are on that graph. So I'm going to present here the positron annihilation spectroscopy method, which is an extremely useful way of analyzing the defects into our samples. And when I say very useful, it's really to say the least, because it has a huge advantage of being extremely sensitive to low defect concentrations. So when we want to do what we do, it's very it's very useful, and it will give a very useful information about what we do to the sample. It has also a downside, which is the limited defect detection size. But in our case, since we want to see how the reaction starts, it's not that problematic. So we add this way of characterization with the XRD X-ray scattering that you have just above here. That is more versatile and will give very complementary information. It also, PAS also has a wide range of depth analysis, and there is one characteristic that I will talk about that is extremely interesting for that regard. So it's very ideal for what we are looking for. Here is an example of installation that we use. So the basic principle is that we have a sodium-22 source. It emits a large amount of positrons. We use a moderator to filter the energy band we are interested in for this positron beam. Then it's filtered with a magnetic field, and we can reach a very wide range of energy, beam energy, incident beam energy. This is quite useful because we can go very deep into the material. So this PAS technique is separated in basically three useful ways. The first one is the positron lifetime spectroscopy. It allows us to have a direct interpretation of the vacancy, the size of the vacancy, sorry. When we do the deconvolution of the positron lifetime spectra, it gives us value of peak and intensities of each interaction between the positron beam and the crystal lattice. So basically we can see the size of the vacancies inside the material. We can see the density of the defects inside the material, even if there are not a lot of them. So this is really interesting for what we're doing. When we do this analysis, we have also the depth profile that we can do. You sweep basically the energy of the positron beam to be able to have an idea of what's at stake and how the defects are distributed along the depth of the material. It has a lot of application, and the one we are interested in is the study of damaged or irradiated material. To give you a little bit of insight of how do we do the lifetime spectroscopy analysis, we have these peaks that are generated by the interactions between the material and the beam of positrons. Basically, we shoot this positron beam and we count the time between the interaction of the positron with the material and its annihilation. So we look at two different peaks of gamma radiation around the sample, and the time resolution will give us a very good idea of how this measurement, or how this beam of positron is interacting with the vacancies and the defects. On the 511 keV line, we have here basic peak showed. We have two different parameters that are extracted from it. The S parameter, which is the most prevalent parameter, will give us the ratio of area under the, will give us the proportional, the effect of S parameter is proportional to the defect concentration inside the material. And the W parameter produces information about the defect, the type of defect, but it has less significance than the S parameter, as was saying Orodek, one of the participants in this research group. Here we have a result that is produced from a zirconium target that we implanted with deuterium and carbon. And then we take this sample and we bring that into the positron annihilation spectroscopy system. What we can see is that, first, one of the first notice I wanted to show you is that this characterization technique has constant systematic error as the energy of the incident positron beam is increasing. So it's independent from the beam of positron that is generated, but it's also very significant because despite the energy beam, hence the depth of which we are looking inside the sample, we really have a constant precision of the measurement. This is very valuable. Here in that case, with the zirconium deuterium carbon system, we can see that first we have a large increase of the S parameter right at the surface of the material, here. And we can see that there is not much difference between the pure deuterium and the deuterium and carbon beam. which gives us an idea that defects have been generated by the interaction between the sample and the beam, but also it doesn't make, in that case, much difference between the deuterium and the deuterium carbon. We also see that there is a dip after the reference is stable. Here we have a dip that goes underneath. This is interpreted as a migration of the defects from underneath the surface toward the surface of the sample. Then I wanted to add that our reference is greatly increasing at the very beginning of the energy of the incident beam. This is due to the metallic state of the original sample that we're using. Hence, I hypothesize that this is due to lamination defect and then dislocation generated by lamination on the very surface of the material. Here I'm presenting the W parameter results. So we have very inverted but similar results as the S parameter. It basically confirms what we have seen before. Here we have a large decrease of the W parameter result that gives us a large accumulation of defects in the surface. We can analyze these defects types by looking at the S parameter over W parameter graphics. And we can see that all these points are basically on the same line. This gives us the idea that all these defects are of very similar sizes. I would also add that we have, for the reference, 2 points that are extremely wide and separated. The widening of this position of these 2 dots is showing that this type of defects is more of the dislocation type. Let's switch system. So now we have a zirconium sample. We irradiated not only with deuterium, but also with deuterium and 2 different isotopes of oxygen. Then we take this sample, we put that into a positron annihilation spectroscopy, and we look at the lifetime analysis spectroscopy of this positron interaction. So here we have a very similar effect, but we can see that the oxygen did not produce as much defect as the pure deuterium beam. So we have a very clear idea that oxygen is actually not producing that much defects, and this is showing how much oxygen in solid solution tends to have a stabilization effect of the dislocation and the vacancies inside the material. I would like also to add a note, because in the previous life I was working on ceramics and spinel materials, and it was exactly the same. Oxygen tends to stabilize and to keep the defects and all the features around it at the same location. It doesn't diffuse very well with oxygen. Here we have the W parameter results. So we have, in the same way, but invertedly, we have this decrease, very sharp decrease right at the beginning, right at the surface of the sample. So we have a lot of defects, and here in that case, we can assess there are vacancies. And we also have all the points that are localized at the same point and on the same axis. And this is a sign that most of the defects that have been created in those curves are monovacancies because they are all of the same size. We can see here that we have an analysis that was done by Horodek from Krakow about the thickness of the defected layer. it's really interesting because we can see that the positron diffusion length, and keep in mind, every time that you have a positron that interacts with vacancy, it actually tends to less interact with the vacancy than any other element. So you're going to have a deeper, and you're going to have more. You're going to have more. You're going to have more energy, and it's going to broaden your peak of 511 keV. So it's very useful system, and there's a lot of information we can extract from this data. So here, for the reference, we have positron diffusion length that is almost double what is the rest of them. This is basically telling us how much and what type of defects have been interacting with the beam. Another part of the explorations that we are engaging is about XRD, and I've been explaining that XRD is complementary to positron annihilation spectroscopy. So here we have zirconium again implanted with monoatomic deuterium, ionized monoatomic deuterium. So it's a beam of deuterons, and it has been used. The sample has been used at 2 different energies with 2 different fluences. And we can see the influence of mostly the fluence on the size of the peak. So here you have, it's very hard to see, sorry, the contrast of this projector is not really good. We can see that the peak between here and here, the size, the height of the peak is pretty much the same. Despite being at 2 different energies, the size is the same, and the size is different. The size is the same, and the fluence is the same too. However, here, when we look at the same energy with different fluences, we have the size of the peak that is greatly influenced. So we have all these peaks that are mostly influenced by the fluence. Sorry for the complexity of that sentence, rather than the energy of the incident beam. So it gives us how the beam is interacting and modifying the crystal structure on the surface. Here we have the latest spectra produced by Agata Kowalska. We can see here that in red we have the zirconium 1.5 phase that has been produced inside the sample. And this gives us an idea of where we end up after the experiment and how the zirconium sample has been modified in terms of hydride formation. So we have a FCC phase when we get into the 1.5. And the evaluated stoichiometry is, during the experiment, during the implantation, is 2. But we take the sample out, and then we go to an XRD, and then we measure 1.5. So my guess is that either there have been some desorptions, or we have to do an estimation of a thorough investigation of the stoichiometry during implantation. So here it's going to be really difficult to see, I think. Oh, actually, no. Yeah, I'm surprised. So I don't know if you can see here, for instance, this zone, this zone, this zone, all this surface that is supposedly laminated. So all should be stripes. There should not be any what looks like a skin effect or modification of the stripes that are induced by the lamination. We have these features that appeared on the surface, and this is typical of phase change, local phase change, especially in the case of zirconium, because of the particularity of zirconium phase change transformation as the hydride forms. We have hexagonal compact, and then we go to a cubic centered phase, and then we arrive to a phase centered cubic. All these transformations drastically modify the structure of the material, and that is exactly what we can see here. I'm very happy about the contrast finally of this projector. One of the project I'm working on is the preloading of the material. So instead of just exposing the sample to the beam and having this long wait time, I would like, since the installation requires a long time of implantation before getting high level of stoichiometry, I would like to have a material that is already preloaded, and knowing the stability of the hydride, it's, I think, a very big advantage. So that's what I'm doing. I'm increasing the temperature of the sample first into a vacuum tube furnace, and then I increase the amount of hydrogen to be able to load the sample within a controlled environment. This way we have a bulk formation of the hydride, and we have less effects of the phase change modification transformation that tends to have these features created. Of course, it creates defects, which is in our advantage, but my job as a material scientist is to have a control, have a way to be able to design things rather than just waiting things to occur. Here we have another observation that is very interesting. So on the spectra that we have seen, we've seen a lot of peaks of the hydride 1.5, which is called the 28 minutes. And we can see here that there are modifications of the surface topology. These modifications to the surface topology is typical from the precipitation of hydride phase on the surface of the material. The other aspect that I think is extremely important is, and I don't know if you can see, all the tiny holes that are all around these precipitates. The reading I have as now quite well bibliographist of the superabundant vacancy is a clustering of the vacancies, and then a migration of those clusters of vacancies to the surface of the material. And I gave you two pictures here of what it looks like. This is from Daniel Fouchard. I don't know if you know him. He's one of the discoverers of that. And this is a very known, well-known reference where we can see the clustering of the vacancies. So we really have a coalescence and a migration. So we've seen that, of course, SEM, but XRD and positron annihilation in spectroscopy are very useful and complementary diagnostics method. Sorry. PAS have a high sensitivity of density vacancies, and that binds to deuteron atom, and XRD is sensitive to the change of crystal structure as well as the formation of the hydride. It's very classical XRD, but it's very complementary in our case. So both diagnostics will be used in our lab. We have seen that vacancies move toward the surface during the irradiation, and we can also see them on SEM. How lucky is that? XRD shows building of delta phase, the 1.5 hydrogen per zirconium atom phase, and we have a large deuteron density observed in the nuclear experiments. So what are our perspectives? We want to have a better control of the material preparation. We want to solve the problem of sample absorption, if really it is. We want to have also an access to different positron lifetime spectroscopy analysis installation. That is my next step. We want to expand the range of metal and alloys to irradiate. We also want to verify the effects of carbon and oxygen implantation on electron screening. And then we want to do replication and new measurements with a gas loading system in our lab to be able to compare what we do with implantation and what we do with gas loading. Thank you. So I took too much time, then I'm going to quickly sweep to, maybe Ivo Morasan. And that's going to be it, okay?
Thank you. Nice presentation. I'd like to ask about positron annihilation spectroscopy. And you show the vacancy diffused towards the surface, right? And in your analysis, you conclude that this defect is not the monovacancy, but the dislocation.
For the reference.
Reference.
Yeah, for the reference material.
Reference material is
it's a laminated plate of the zirconium.
Understand.
Lamination doesn't create any vacancies; it just creates dislocations.
Okay, I got it.
Yeah, cold rolling. It's
Okay.
cold rolling and
Cold
lamination.
roll sample mainly. Okay, got it. Thank you very much.
Zirconium has 40 electrons. Zirconium has 40 electrons.
That's a good question. Is it a question?
It's the beginning of question. You just stopped me. How much the screening? Is it coming from every?
How many valence electrons?
No, I mean the screening effect. Is it coming from every electron in the zirconium?
Every electron in the zirconium, even the lower shells?
Yeah.
That's a very good question.
No, I mean you were talking about affecting.
You have my boss that is very happy to answer your question if you
Yeah.
may.
Main contribution to the screening is coming from the conduction electrons. So there's not zirconium electrons, but there is maybe 10, 20, 30%. It depends on the metal, hosting metal, and there is a polarization of the bound electrons of zirconium of these hosting atoms as well. So we see both. We see screening coming from the conduction electrons bound to the deuterons and bound to the hosting metal atoms as well. So we have different contributions, you know, and yeah, there are many details of the model or calculations we made. So definitely we see large contribution from this metallic hosting metal as well.
Thank you, Mathieu. Perhaps, as usual, I have missed the main point, but why zirconium? I mean, what do you believe it is interesting for the future application that we are discussing here in the workshop? And finally, third question altogether, which is the possible study of situations that are much more complicated as the structure is not so nice as what you have presented here. I mean, not a real crystalline structure or something like this.
Not real crystalline structure?
Yeah, if you don't have a crystalline structure
well, we need
for other materials, of course.
As Conrad was answering just before, we need to have a metallic structure, okay? That's very important because we need free electrons. These electrons are necessary part of the screening energy enhancement, okay? Why we use zirconium is simply because zirconium binds to hydrogens and deuteriums bind to zirconium and are stable. So in terms of experimental conditions, it's much easier than using palladium, because palladium you implant hydrogen or deuterium inside, you stop the beam and everything goes away. Matei has a...
Zirconium is a possible candidate for our kind of experiment.
It's a test tube experiment. We are not in the situation of attempting to have a production material as using zirconium. It's as many say now, the host material is really a host. The big advantage also with zirconium is that we can reach level of stoichiometry that is really high. So we have a lot of protons and deuterons, especially deuterons, sorry, inside the zirconium, and this enhances the effective electron mass. So more we have deuterons inside the structure, better it is for us.
And what about titanium?
Well, titanium is also very interesting. I think it's less interesting as zirconium for the reasons that titanium binds very well with the deuterium. However, the phase change triggers production of powder. Yes, it depends how much you load it with it. I don't want to risk it with the accelerator because we have very high, expensive turbo pumps, and I wouldn't be happy if it does. It's literally just below the sample holder. Yes, that's maybe one candidate. Conrad has been studying already in the past this material. Mm-hmm. Okay, thank you. Okay. I would like now to call my colleague, my friend, Jacques Ruher.
So, thank you, man. Well. So, thank you for listening me again, you know. We are talking from a very different subject, and as yesterday, I'm assuming that it works, that you know how it works and why it works, and I am going to tell you what we can do with it again. So, as you remember, maybe, for me, these reactors, this is a black box. You see, this is a black box, and you have an excitation here going in. You consume electricity, to make it simple, and you get heat out, you know, with some heat losses at every step. Of course, this heat can go into a heat converter. The heat can be used directly or indirectly via a heat converter. Why not an electricity generator? And if you produce electricity, of course, you can feed back some of this electricity up to the entrance to excite more reactions. Fine. Now, there are several ways to do it, and this is what we are going to discuss now. I make a distinction between different types of systems, you know, and this is a temporary discussion, classification that just valid this morning. Type 1, this is a system in which you need excitation, but you have to heat up the system as well. Type 2, you don't need to reheat it, you just excite it and it goes. Type 3, this is an electrical generator, so now it produces electricity enough to supply its own excitation system. And most probably in the future we will have, at least the society will automatically make a distinction for type 4 with all solid state technology, but we are not that far for the moment. It's for the future. So let's look at this type 1 system. You need to hit the machine and to make some excitation with some heat, of course, and exergy excitation. Exergy, what is exergy for me? This is any form of energy other than heat. So it can be, you know, electrical discharge, DC current, hydrogen pumping, making of magnets rotating around, anything you imagine except simple heating. And it has an importance because if you have a system you just operate simply by heating it up, preheating it slowly at the beginning, you have to make sure how to make the control of the system, you know, because it is the dragon's tail, and you have to make sure that you can control it. So you have to tame the dragon via proper cooling, you know. Otherwise, if you don't that, you get a runaway situation. And you laugh, but maybe if you have a memory, you saw these pictures already in the past. Because you know, do you remember how you can escape this runaway situation? I explained it already. Who remembers how to escape the dragon? Nobody. I am preaching in the desert, you know. Because this is the way it goes. If you draw the temperature, the heat output of your system against the temperature, normally speaking, you have such a heating curve, you know. This is a power curve. And now to avoid the problem, you have to cool it with a cooling system like that. It means you have to cool the system hardly with a hot fluid. You don't cool it with cold water. We cool it with a very hot fluid, almost at the same temperature as this reactor. And if you look at my past publication, you will find why it is stable in this case. But you know. And this is the operating point, and at the end you export the heat at this temperature. Not at this one, but at this one. Anyway, so just to say that if you have a reactor working simply because you heat it up, you have to take care of the cooling system. Now, if you have some exergy, it's easier, you know, because you just feed the dragon slowly and you control it easily. Now, some definitions. The excess heat, everybody agrees this is the heat output minus the heat input. Well, which one? Which one or this one? We have to make sure if we are talking about the heat energy input here or here. This is already a little bit different, you know. And the coefficient of performance is worse. This is the ratio between this heat output and what? The heat, the energy input. And I also like to talk about the amplification factor. This is indeed the heat, the additional heat you get compared to this exergy input. Because if you change the thermal insulation of your system, you change the situation, you know. With a low thermal insulation, you need to heat it up. If you have a good insulation, you don't need heating anymore. So you see the difference. And if you have no insulation, you need a large heating. If you have a good insulation, you have less heat, of course, because you don't have the heating system anymore. But the amplification is kept. The coefficient of performance is changed. So when you speak about the coefficient of performance, you have to make sure what is the heat output This is known. But what is the heat input you take into account, you know? And not everybody agrees on these definitions. And how you count the supply losses, the losses of this excitation system. Now, how to make, what is next? This is a type 2, you don't need to heat it because it works just by exergy input, and you have some heat for use. The heat losses, maybe, we love that in the industry, can also be recovered as much as possible. And what is the difference between a type 1 and a type 2? Mainly, this is the size of the reactor. If you have a small reactor, you have a large surface compared to the internal volume, and you have large losses. Now, if you have a larger reactor, you know, you produce so much heat that the heat losses are not sufficient to cool. You need to cool it additionally, and this is what you want to do. Same thing if you have in your lab a small cell, you need to heat it in an oven, you know, to make it work. But if you make a cluster of even the same cells, the same one, but if you make a cluster of many, many cells, well, the temperature goes up much easily. Now, this is on the way to type 3. You can take this heat coming out to a thermodynamic energy converter, and this electricity can be fed back to the excitation. But in this case, you know, it's not enough. You still need some electrical input. So even in this case, this is for me a type 2 system, because you still need some electricity in to get what you want out. Now, of course, if you have enough electricity coming out of this converter, you can export some electricity. You have enough electricity for excitation, and then this becomes a type 3, except maybe some electricity to start up, because the difficulty is to get the first reactions, isn't it? Now, what are the conditions for the self-sustained operation? This is a very complicated formula, you know. The heat output minus the heat losses multiplied by the conversion efficiency of your converter must exceed what you need for excitation. And if you consider thermodynamic converters, the efficiency is governed, as you know, by this Carnot theorem, you know, but it's not enough, because no thermodynamic engine is able to reach this theoretical limit. So you have to accept to multiply this theoretical efficiency by a relative efficiency, which depends heavily on the type of machine you have. For example, a steam turbine, you are happy with 0.65. Thermoelectric converters, the most modern ones, reach 0.3. Stirling 0.6 and so forth. I don't know if you ever heard about Johnson thermoelectrochemical converters. Do you know this thing? You know, Georges? No? No. We may have to hear much more in our community about this, because this is a solid state converter able to reach very high relative efficiencies. So keep this name in mind. You may hear much more about that in the future. So you know this, the Carnot efficiency depends, of course, on the absolute temperature, and all the other curves are below that one. And also, when you select a converter, the efficiency is not the only point to take into account. You must know how to make the coupling between the heat source and this converter. Is not that easy, depending, for example, a steam turbine is able to work only between a limited range of temperatures, even if it is extending now up to 700. A Stirling engine is limited as well. And if you look at modern nuclear reactors, you know, some are thinking about liquid metals, liquid salts, gas cooling, and so forth. So it's a whole story we will have to discuss in the future. Once again, we know all the operating parameters of your reactors. And at the end, if we want sustain operation according to this reactor temperature and according to the relative efficiencies of your machine, of your converter, these are the COPs you must reach to get to obtain a self-sustained operation. So for very good converters, indeed, COP of 3, 4 at 300 degrees, 400 degrees may be enough. Now, if you want to use thermoelectric converters, you know, you need much higher COPs before making it run on its own. Conclusion, we can make a distinction between type 1 and type 2, and as long as we are talking about lab rats and laboratory experiments, because the type 1 are small things we have to heat. But all useful heat sources, of course, delivering heat will probably not have to be heated. You know, if we tell a customer you are going to give you heat provided you heat it up, it's hard to sell. And the distinction between type 2 and type 3 is given by this output, heat or electricity. What am I going to get, heat or electricity? So, most probably, the classification will be simplified in the head of people as heat sources or power sources, you know. And maybe it's not forbidden to find better names for the same thing. Thank you for your attention.
Thank you for your talk. I have realized something what is really strange for our community, because this is something what is, if we compare our cold fusion future reactors to the fission reactors, there is something what is very dangerous. So if you, at least for gas loading experiments, you have a positive temperature coefficient. It means that energy production increases with the temperature increase. So it is something what we want to avoid in fission reactors. So all modern fission reactors work with negative temperature coefficients, and we are looking for some inherent safety features here. So heat itself cannot be a very good solution for control of the gas loading systems here. So maybe we should think about pressure as an additional parameter. We can reduce the pressure during the operation, pressure of the gas, that can put down the reactivity of this reactor, gas loading reactor we are speaking about. So this is really something. Of course, there is not danger compared to the fission reactors. We can also melt down the core, so we have a safety or emergency situation, you know, accident situation that you can finally melt down the core. It's something what we should think about as well, you know.
I don't want to discuss too much about nuclear reactors, because it's true that most nuclear reactors have negative temperature coefficients, except, you know, breeders reactors, which have positive condition, some of them. Anyway, in our case, you said, why not control the system with the pressure? Excellent. This is just an example of exergy control. You pressurize the system, you depressurize the system. This is a control by exergy, let's say, parameter.
But we should have a so-called inherent safety features. It should be controlled by physics, you know, by...
This is the reason why I said a good system. This is not an invention, what I presented. You know, if you, in the chemical industry, I don't know if you know the Fischer-Tropsch reactors, you know, you inject carbon monoxide and hydrogen into a chamber with catalyst, and you get out of it methane, hydrocarbons, and things like that. The reaction is highly exothermic. And you have to keep the temperature, because instead of getting gasoline, you are going to get, with a high value, you are going to get methane with a much lower value. So they have to control the temperature within a few degrees to get the products they want. And they do it exactly like that, with a very hard cooling, with a hot coolant. Exactly. This is no big deal.
I don't think the Carnot cycle applies to thermoelectric converters because there's no cycle there.
Sorry?
When you have thermoelectric converters, you cannot apply Carnot because there's no cycle.
Oh, you have to.
You cannot.
You do?
No.
We talk about it.
We have to go back to the books.
With pleasure.
Just bear with me, I'm not using this, hopefully. I can sing you a song. Round like a circle in a spiral, like a wheel within a wheel, never ending or beginning on an ever spinning reel, like a snowball down a mountain or a carousel balloon.
Stiamo provando ad attaccare un altro computer via HDMI. Abbiamo già collegato tutto.
Okay, so whilst we're trying to fix this, I've got a question for you. Does anyone here know what a toroidal dipole is? Anyone? Hands up? I won't bite. Okay. Does anyone know what an anapole is? Anapole. Anapole. An apple. I know what an apple is. Yeah. Okay. So an anapole was something proposed by Zeldovich in 1957. It's critical to what I'm going to be talking about today. And the toroidal dipole was derived in a thesis in 1965 by a researcher at the Dubna Nuclear Physics Research Center in Russia. The name of the guy was called Dubovik, and you'll see that I got to that through a very circuitous route. But essentially it kind of completes electrodynamics, and it wasn't recognized in the West until 1997. I think at Caltech they found the toroidal moment in two element isotopes. And it is barely recognized by the physics community worldwide even today. I hope maybe, if I can get this working, that you will see that maybe this is an extremely important thing to consider. You may not think that, or something else. Oh, that's going to be fun. Okay. All right. Not like that, though.
Convert in PowerPoint.
I know, it just won't have any of the videos. But it's okay. I kind of predicted this. So. All right, so we're going to miss a lot of material, but you'll probably enjoy the fact that that happens. Okay. Right. Has that still got power? Anyone know what the toroidal dipole is yet? No? I'll use my memory stick here. Best laid plans of mice and men. Okay, we'll try this.
It's a PowerPoint?
No, it's not. It's no, it's not. it's but I can make it a PDF. I can make it a PDF. Okay. Okay. So if you haven't seen the Ultra experiment, it came about by accident completely. What happened was, we had some indium that I selected for the purpose of testing whether there were some weak interactions in the vibration system of one Dr. Ruishin Amasa in Tokyo. And, okay, so here, the most recent PDF, we can see. Okay, so this indium I chose for a number of reasons. I've spoken about some of them during the week. One is it is a neutron absorber. It's about the same as gold. Two, it has almost entirely a beta isotope. And if we're going to look for weak interactions that are very effective, we want a long-lived beta isotope to see anything occurring. It had a low melting point. That was very critical because we're going to be applying Amasa gas later on. And it was very soft. So I thought if there was any cavitation in the cavitation system, that when the bubbles came out and hit the indium, it would leave very good impressions on there. And in fact, much of what we would have wanted to come out of that came out of it. But that's already been shared.
It doesn't work.
What doesn't work?
I don't know. So yes.
Oh, maybe it was working, but you needed to turn that back on. Okay. Okay, all right, make the coffee break, we'll have it sorted. Do you need to turn that on? Do you need to turn it off on and on between?
Yeah, I do. It tried. But did you usually use the HDMI on
Yes, yes, I use it.
Yeah?
Yeah. So it maybe needs to reset. Maybe it's looking for a particular... Take a bit of time to warm up.
Yeah.
È strano però perché
Oh, is that the actual video?
yeah, it's active repeater to the projector. I don't know if adesso vediamo. Speriamo che una persona scarica di corrente da. C'ho questa preoccupazione. Speriamo di no.
Is your file in?
It's on my own membership.
Ah, okay.
Il programma qual è adesso?
No, quella è una cosa orribile. Volevo... Magari lo inventiamo... Sono arrivato troppo tardi. Oh signore, scriviamo bene.
No, è che il problema, a meno che fosse rotto il proiettore. Non è chiaro la corrente. Cioè il programma che serve. Vabbè. Ma intanto il proiettore fa là.
Speriamo di segnare.
Okay. So can we try it now in here?
There's a problem. I captured the screen from this program. Okay.
Okay.
Vmix. And I stream and recording by.
Okay. Let's see what
with
my
the presentation in this PC.
I understand.
Okay.
And you do it on Vmix here. Okay. I mean, I use the streaming software on here, but not Vmix.
If you want, cioè io se vuoi cioè gli riprendo lui e lo schermo e mando in onda quello. Questo computer. We can try to connect your Mac.
Non attaccare ancora, perché ho paura che qua non c'è la terra. Possiamo cambiare questo?
E questo che è? Ah, sì,
quello sia il computer. Posso attaccarlo?
That's mine.
Questo va bene, questo not the correct way.
Wow, yeah, I know.
Because there was no air, no jam.
Uh-huh. Maybe it tripped it.
Yeah.
Okay, so...
I kill
Ah?
L'avevo attaccata io, ma quella l'ha attaccata lui. No, non l'aveva fatto. Allora, prima di attaccarlo,
It saw the screen earlier. It saw the screen.
now it works.
Yeah, okay.
It worked. Now we don't know if
Che è stato cambiato il computer, il programma
Ma chi
che
è cambiato?
che lui vuole usare il suo perché ha tutte le sue cose.
Giorgio,
Yes.
però hai distrutto una mattinata. Se è così lo fai per ultimo, capito?
No, not at all.
E lei puoi fare come cazzo di pare.
auto questo, no?
È un cuffio, sì.
Yes.
Poi perché quello
Okay.
dopo adesso dobbiamo rifare tutta la pippa, no? Chi gli ha dato questo permesso?
Pensavo fosse veloce, perché invece non andava.
No, quando è così avvisami e la reazione fa per ultimo.
Il problema è che non
Okay, Canon, standard.
Ok.
It sees it. This is it, yeah?
Yeah.
Done. Extended display.
Yeah.
Okay, done. Right, so...
Okay.
With this.
Perché adesso lui se ne va.
It's this one here, this one here.
Sorry. Yeah. Scaled.
Okay, that one. All right. Do you know what resolution it is? That one.
Show
isn't it?
resolution.
Ascolta, Gio, ascolta.
1 minute.
Your is the last because we started to again.
We have to change it back
Change.
after.
Okay.
Because
the
the
next question.
half
Okay.
an hour to put again. You remain here,
Okay, all right.
okay, and we change the Mi metti quello
perché non funziona? No? Questo è acceso.
It's got it, it's got it. Okay. All right. If you move this out, I didn't load it, so maybe it's too big for it. So if we eject this, I will try and get it working on here. Something.
Yeah, just go on questo PC.
No, not to do that.
You want to start?
Listen to me. After the lunch.
Non ho capito perché. Non lo so. Non uso i Mac. Io
No. I'm going to put it on PDF.
Quello è il cavetto che collega al computer l'entrata.
Ok, sì.
Quello è l'alimentazione, questo è un convertitore USB tutto perché i Mac non hanno porte.
I'll try and save it.
Capisco perché non.
Adesso li mettiamo a posto.
Per forza. Ma sì, stiamo facendo un attimo. Non capisco perché non vede quella mano. Forse perché c'è di mezzo. Stavolta la carica c'è. Ecco, ok.
That's so disappointing. I know. I don't know why.
No. It's very strange. You can convert in PowerPoint.
I'm trying. I tried it once. It didn't work the first time.
Oh, because you have also video.
Yeah, I know. That's my problem.
Is that video?
Maybe. Hold on. Maybe. Oh, he wants that. There is video.
Capisco perché è strano perché di fatto si collega. Non è che magari manda una risoluzione altissima. You have the output.
No, don't.
Yeah, this.
The audio, yeah.
The audio. I try to give you a converter.
Okay. All right.
Do you know the resolution you are sending the video?
It's whatever it needs to be. It'll change.
Ah, really?
Yeah. Now I'm not going to get a coffee. And you. Poor you. It doesn't seem to be picking this up. I don't know why. Is it plugged in?